Physics is often described as a system of laws. The phrase is used so casually that it rarely draws attention to itself. Laws of motion, laws of gravity, laws of thermodynamics. The word appears in textbooks, lectures, documentaries, and casual conversation, carrying with it a sense of authority and certainty. It suggests that nature is governed in the same way societies are governed, by rules that command behavior and enforce outcomes. But this familiarity hides a problem. In physics, laws do not behave like laws. A law, in the human sense, implies authority. It implies enforcement. It implies that if the rule is broken, something intervenes to restore order. Human laws require institutions, mechanisms, and consequences. They operate by compulsion. But nothing like this exists in the universe. There is no agency that enforces Newton's laws, no mechanism that compels particles to obey Maxwell's equations, no authority that ensures energy is conserved. There is only behavior. Patterns in what happens, regularities that persist long enough for us to notice them. This difference matters because the word law quietly suggests a causal role that these mathematical descriptions do not actually play. Electrons do not move the way they do because an equation tells them to. Planets do not follow orbits because gravity commands them to comply. Nature does not consult formulas before acting. The equations come later. They are written after observation, not before. They summarize what has been seen. They do not prescribe what must occur. In practice, what physicists call a law is a compression of experience. It is a way of expressing, in a compact form, the regularities observed across many experiments and measurements. When the same pattern appears again and again, it becomes tempting to treat the pattern as a rule. Once it is named, it begins to sound as though the name explains the behavior. But this reverses the direction of explanation. The behavior comes first. The law is inferred afterward. This reversal is subtle, but it has consequences. When we say that an object falls because of the law of gravity, we are not identifying a cause in the physical sense. We are restating the observation in a different language. The law does not add a mechanism. It provides a description that allows prediction within a certain domain. It tells us how things tend to behave, not why they must behave that way. This distinction becomes clearer when the regularities break down. In classical mechanics, the laws appear strict and deterministic. Given initial conditions, outcomes can be calculated with precision. This makes the language of laws feel natural. But even here, the sense of enforcement is an illusion. The equations describe an idealized system. Real systems always involve approximations. Friction, uncertainty, measurement limits, and environmental interactions all complicate the picture. The law is never violated because the law already includes the conditions under which it applies. Outside those conditions, it simply stops being relevant. At smaller scales, the mismatch between the word law and physical reality becomes harder to ignore. In quantum mechanics, outcomes are not determined in the way classical intuition expects. The laws do not specify what will happen in a particular event. They specify probabilities. A particle decay has no cause in the classical sense. There is no hidden trigger that determines the moment of decay. The theory provides a statistical structure, not a command. It tells us how often certain outcomes occur across many trials, not which outcome must occur in any given case. Calling this a law stretches the word close to breaking point. A rule that allows multiple incompatible outcomes is not a law in the usual sense. There is no violation when a different outcome occurs. All allowed outcomes are consistent with the same mathematical structure. The regularity exists at the level of distributions, not events. What is constrained is not the individual occurrence, but the range of what is possible. The same pattern appears in relativity. The equations of space-time do not enforce a single description of events. They allow multiple, equally valid perspectives. Time intervals depend on the observer's state of motion. Lengths contract. Simultaneity dissolves. The law does not dictate a unique outcome that all observers must agree on. It defines relationships that hold across different frames. What is preserved is not a particular measurement, but a deeper structure that constrains how measurements relate to one another. Once again, the law does not command behavior. It limits inconsistency. It defines what cannot happen rather than what must. No observer can measure a speed faster than light. No transformation can produce contradictions in causal order. These are constraints, not instructions. The equations map the boundaries of coherence. The tension becomes most obvious when our theories fail to coexist. Quantum mechanics and general relativity are both extraordinarily successful within their domains. Each is supported by overwhelming experimental evidence. Each produces precise, testable predictions. And yet, when applied together, they do not agree. There is no single set of laws that governs all scales. The attempt to unify them reveals contradictions that cannot be resolved by extending either framework as it currently exists. If laws were truly fundamental rules imposed on nature, this situation would be difficult to explain. One would expect a single, coherent legal structure underlying reality. Instead, what we see are overlapping descriptions, each valid within limits, each breaking down beyond them. The failure is not random. It occurs at specific boundaries where assumptions built into the laws no longer hold. This pattern suggests that what physics discovers are not laws in the legislative sense, but constraints imposed by deeper structures. The equations work because the universe exhibits certain regularities, not because the universe is following orders. When those regularities change or dissolve, the equations lose their grip. The idea of constraint provides a more accurate way of understanding what physics achieves. A constraint does not cause behavior, it restricts it, it defines what is not allowed. Within those limits, many outcomes remain possible. This is how physical theories operate. Conservation laws do not force energy to be conserved. They express the fact that no observed process violates conservation within the relevant domain. If a violation were observed, the law would not punish the system. The law would be revised or abandoned. Reversibility is telling. Human laws persist even when violated. They remain laws precisely because violations occur. Physical laws do not work this way. A single reproducible violation is enough to undermine them. This alone should signal that they are not laws in the same sense. They are provisional summaries, contingent on observation. Symmetry principles make this even clearer. Many conservation laws arise not from direct observation of conserved quantities, but from symmetries in the mathematical description of systems. Time translation symmetry leads to energy conservation. Spatial translation symmetry leads to momentum conservation. These are not commands issued by the universe, they are consequences of invariance. If the structure of the system does not change, under certain transformations, certain quantities remain constant. The conservation follows from the constraint imposed by symmetry. Nothing in this picture resembles enforcement. There is no mechanism that ensures energy remains conserved. There is simply no allowed process within the theory that would violate it. The moment such a process is observed, the theoretical structure changes. The constraint shifts. This view also clarifies why physics often advances by identifying failures. When a law breaks down, it does not mean nature has become inconsistent. It means the description has exceeded its domain. The breakdown reveals a boundary. It shows where assumptions embedded in the law no longer apply. These moments are not anomalies to be ignored. They are the most informative points of contact between theory and reality. Historically, progress in physics has often come from precisely these failures. classical mechanics could not account for black-body radiation, leading to quantum theory. Newtonian gravity could not explain the precession of Mercury's orbit, contributing to general relativity. The ultraviolet catastrophe was not a minor discrepancy. It was a signal that the conceptual framework had reached its limit. Each time, the failure was not a rebellion against law, but an exposure of constraint. Language, however, lags behind understanding. The word law remains in use because it is familiar and convenient. It carries rhetorical weight, and it conveys reliability. But it also smuggles in assumptions that physics does not support. It suggests that reality is governed rather than structured. It implies that behavior is compelled rather than constrained. This matters especially when physics is communicated beyond its technical context. Popular accounts often lean heavily on the implied authority of laws. They speak of the universe obeying rules, of nature enforcing order, of equations governing reality. That language makes the success of physics seem almost mystical, as if mathematics were written into the fabric of the universe, as if equations existed independently of observers. But mathematics is not discovered in the universe in the same way particles are. It is constructed as a language for describing patterns. Its effectiveness lies in its ability to capture regularities compactly, not in its authority over matter. When mathematics aligns with observation, it is because the structure of reality allows such alignment, not because reality is following mathematical instructions. This distinction becomes crucial when dealing with the limits of explanation. If laws are taken to be fundamental commands, their failure demands replacement by deeper laws. This encourages an endless search for more comprehensive rulebooks. But if laws are understood as boundary descriptions, their failure points to something different. It points to changes in structure, to transitions where the very notion of description must be revised. In this view, physics is not a hierarchy of laws stacked on top of one another, each more fundamental than the last. It is a map of constraints, each valid within a region, each marking where certain kinds of behavior are possible and others are not. The map grows by refinement, not by accumulation of authority. Even the most celebrated laws in physics reflect this. The second law of thermodynamics, often described as an inviolable principle, is statistical at its core. It does not forbid decreases in entropy. It makes them overwhelmingly unlikely in large systems. The law expresses a constraint on probability distributions, not an absolute prohibition. At small scales, entropy can decrease. There is no enforcement mechanism preventing it. The law holds because of numbers, not commands. Seen this way, the universe is not ruled, it is structured. Order emerges from constraint, not obedience. Stability arises from permitted configurations, not enforced ones. The regularities we observe are consequences of what cannot happen, not instructions dictating what must. This perspective also reframes the role of explanation. To explain a phenomenon in physics is not to identify the law that forces it to occur. It is to show how the phenomenon fits within a set of constraints, how it does not violate conservation, symmetry, or consistency. Explanation is about compatibility, not compulsion. When this is forgotten, confusion follows. The search for ultimate laws becomes a search for authority where none exists. Questions about why the universe obeys laws become misplaced. The universe does not obey. It exhibits patterns. The patterns persist because of structure, not submission. Recognizing this does not diminish physics, it clarifies it. It places its success on firmer ground. The power of physics lies not in discovering commands written into reality, but in identifying the boundaries within which reality unfolds. Its achievements are maps, not decrees. Calling these maps laws is a historical habit, not a conceptual necessity. The word has endured because it conveys reliability and predictability. but it also obscures the provisional descriptive nature of what physics actually does. It encourages the illusion that certainty resides in the equations themselves rather than in the limited domains where they apply. When physics encounters its own limits, this illusion becomes a liability. The breakdown of laws is often interpreted as a crisis, a failure of understanding. But from the perspective of constraint, breakdown is expected. Every description has boundaries. The important question is not why a law failed, but what its failure reveals about the structure it was describing. In this sense, physics advances not by discovering new rulers of reality, but by tracing the edges of what reality allows. Each theory outlines a region of coherence. Each law marks a boundary. Beyond it, new constraints apply. The universe does not need laws to function. It does not consult equations or enforce rules. It simply exhibits behavior within a structured space of possibilities. Physics steps in afterward, measuring, abstracting, and describing those structures as best it can. Seen clearly, the word law is not wrong, but it is misleading. It points toward order, but suggests authority. It implies enforcement where there is only limitation. It hints at governance where there is only structure. Physics does not govern the universe, it maps it. It traces the contours of possibility and impossibility. It tells us not what must happen, but what cannot. And within those constraints, everything else unfolds. Order exists, regularity persists, prediction is possible. But not because the universe follows laws, because the universe is constrained in ways that allow patterns to emerge. The laws do not rule reality. They outline its limits. And those limits, not the laws themselves, are where physics actually begins.